Okay, hey, welcome back. This is 2.4. We're going to talk about continuity as well as one-sided limits. So just very briefly, what is continuity? Continuity is the ability to draw something without having to actually pick up the pen, right? So here's my xy plane, and this would be some sort of continuous function right here. Okay, so I could draw it without picking it up. What are some examples of non-continuous? So if there's like a hole in it anywhere, then it'll be not continuous, right? Also, you can have kind of the asymptote version. So here it's going to infinity, and then from the right it's also going to infinity. So that's another kind of discontinuity, because you obviously have to pick up the pen to draw the other part on the other side of the asymptote. Another type of discontinuity is the jump discontinuity. Okay, so you would go right to there maybe, and then maybe you have to jump down here to get to the rest of the graph or something like that. Okay, these first two discontinuity types, or the first discontinuity type is considered removable. Okay. In particular, you could kind of define the function by filling in that dot. So you could say something like f of x is equal to, just plain old f of x everywhere except at that one hole. So x, maybe this is the point 2, so x not equal to 2. And then, what a coincidence. Then you put it at like I don't know what this value would be. Maybe it's also 2. Let f of x equal 2 when x is equal to 2. Okay, so you could then that would fill in that dot, and it would be continuous. So that's one reason why they kind of call it removable. It's fixable in a sense. Okay, the asymptote version is non-removable. There's really no way to fix it to make it continuous. And this last one is sometimes called a jump discontinuity, and it also is non-removable. Okay, so you can't fix this one either, just by defining a new point. Okay, so this over here is kind of a fix. Okay. So if you fix it, it's removable. If you can't fix it, it's non-removable. And those are the two. Okay, so anyways, let's get into the actual notes here and talk about continuity. Okay, so the first, these are usually introduced as continuity at a point, right? Continuity on an, so they have this kind of point-wise definition, continuity at a point. But they'll also consider it on an open interval. Usually it's more of a point-wise type definition. So we're not going to write out, well, if it's continuous, that means we could draw it without picking up our pen, because that's really hard to verify, right? Especially if you have a big long function that goes on to infinity. How am I going to verify that, right? So we have this other criteria, which is in terms of limits. Okay, so the criteria for continuity at a point C, and first off, f of c has to be defined. Right? So there has to be something going on there. Secondly, the limit as x goes to c of f of x has to exist. And then thirdly, the limit as x approaches c of f of x, they want that to actually equal f of c. All right? So with limits, you kind of care about the approach, and you don't really care about what happens exactly at the point you're approaching. Right? Because you could have limits that don't necessarily converge to the actual functional value. So for example, if you have this character like this, and maybe it's defined down here, the limit will not be f of whatever this value is, f of maybe 1, right? The actual limit will be this point that's a little higher. So maybe f of 1 equals 1, but the limit of f of x as x approaches 1 is actually 2. Right? So the limit of f of x as x approaches 1 equals 2. So in this case, it would be discontinuous. Right? Okay, so ultimately, if you can do a sub, if you can do one of those limits where you just substitute in the c value and it evaluates, then it's pretty much continuous. Okay, so if you could do a substitution to figure out the limit, then it's continuous. So things from the laws from the previous section kind of point towards functions which are continuous. So polynomials, you can always evaluate a polynomial's limit by just substituting in the value. Rationals, except clearly where the denominator is equal to 0. Everywhere else, you can evaluate the limit just by doing a substitution. Transcendentals, in particular the cosine and the sine functions, cosine, sine, e to the x, those guys don't have any asymptotes to speak of, so they're going to be continuous everywhere. And when we saw that the limits, you could always take the limit of those guys just by doing a substitution. So you know, those are continuous. Okay, so that's continuity at a point, which doesn't seem very powerful, and you know, it depends on the context. But we would prefer continuity on an open interval, something more global. And for right now, the only way to really establish that is to make sure it's continuous at every point in some interval. Okay? So it must be continuous at every point in, and we're talking about an open interval, so open parentheses, maybe a to b, right? Some interval a to b. Okay, there are other ways to define continuity in terms of inverse functions, but we don't really do that here. If you keep taking math, you'll see that in like real analysis or a topology class, I think. So keep taking math if that's what you like, but okay. Anyways, the book gives us a nice figure that helps us kind of wrap our brain around these different types of continuity. Let's see if I can find where that is in the new book. I'm looking, hold on, I'm almost there. It's on page 94. Okay. At least if you're watching this in the future, it might not be on page 94. I just wrote 95, and I meant to write 94. Okay, so let's clear that. Okay, so anyways, let's look at the figure, and it's talking about discontinuity, and it's giving us some open intervals from A to B, and then a function over top this open interval. So let's just put some dashed lines there, and we're starting at A, and then there's some sort of issue here, and then it's going back up to maybe B, so at C there's an issue. So what's the issue here that causes it not to be continuous? And it's number one, the first criteria. F of C is not defined, there's just a hole there. The limit exists, okay? There is a limit, but F of C is certainly not defined, so. So this is not continuous. And in fact, it's a removable type discontinuity. Again, you could redefine it in a piecewise form. and kind of fill in the dots. So it's f of x everywhere except at c, and then you just make c equal to, excuse me, the height of that open dot. Okay. Let's look at another one. This one is the jump discontinuity type, which is non-removable. Okay, so again, same sort of setup. And we have C here. And this one is filled in, and then it goes like this. So in this case, f of c is defined. So f of c works. The problem is that there's no limit. The limit of f of x as x approaches c does not exist. In particular, it has different left-hand and right-hand limits. Okay? And when you have this kind of jump discontinuity like this, it'll be called non-removable. There's no way to fix it. Okay. Let's look at another one. So here's A and here's B. And then C somewhere in between. It's similar to the first picture, except they're actually defining C to be below what you would think it would be. So here f of c is defined. The problem then, well, the limit exists. So the limit as x goes to c of f of x exists. The problem is that the limit of f of x as x goes to c is not f of c. Okay? It's above whatever the heck f of c is. So f of c on the graph is at this point here, okay, on the y-axis. Maybe that's some point D, right? The limit, though, is going to be this point, the open dot, right? So that would be maybe some E. So it fails the third criteria for being continuous, okay? Okay, so that's that idea. There's also the infinite discontinuity case from above here, this non-removable case, which isn't in the figures, but it's also a discontinuity type. Okay, let's move on. Look at some examples from sort of homework type problems. F of x equals x all over x squared minus x. Okay, so what are the discontinuities, and then what type of discontinuities are there? So we take the denominator and set it equal to 0. Okay, and those will be discontinuities. So we have x times x minus 1, 0. So we have two discontinuities, the one where x is 0, and then the one where x is 1. Okay, so this is telling me my discontinuities. Okay, so the title there, so my reader knows what I'm doing. Well, once you figure those out, you have to determine the types. And usually for a rational function, this is the following work you need to kind of do. You want to factor that denominator. And then it'll be a removable type if you can kind of cancel out that particular factor that gave you that particular discontinuity. So you can remove the x over x and be left with 1 over x minus 1. The x minus 1 part, which would correspond to this part I'm boxing in at the bottom, will be an asymptote. Okay, so it'll be non-removable. The part that I removed, the x over x, then corresponds to the other discontinuity, the x equals 0. And when you have that x over x or whatever over whatever situation, that will be a hole in the graph. Okay, so the actual graph, if you were to draw it out, there's going to be an asymptote at 1. And that's where the non-removable discontinuity is. But there's also going to be an issue at x equals 0, okay, which will be y value -1. That's where the hole is. Okay, so this would be removable because you could always define the function to be -1 at that point. So you could redefine it to be continuous at that point. And the way you would do that, you would just say f of x is equal to x all over x squared minus x when x is not equal to 0, and then -1 when x is equal to 0. Okay. Okay, so let's look at another one, another example. So we have f of x equals x over x squared plus 1. Okay. Where are there any discontinuities? So it's kind of a trick question. You may naively try to set the denominator equal to 0 to look for the discontinuity, right? So I don't know, right? You try to solve for, oh, there's no number that I square in the real numbers that's going to give me -1. So there are no discontinuities in this case. So it's a bit of a trick question. You could have jump discontinuities, so something like absolute value x minus 2 all over x minus 2. As a piecewise function, what is that? Well, it's negative x minus 2 all over x minus 2, which equals -1 if x is less than 2. And then it's x minus 2 over x minus 2, which equals +1 if x is greater than 2. So the picture in this case, we have -1 and 1. So when x is less than 2, it'll be -1 right here. And then if x is greater than 2, it'll be +1. Okay, so we have a hardcore discontinuity at x equals 2, and it's non-removable. There's just no way to kind of redefine it in order to fix the problem. Okay. If you have any asymptote, that will be non-removable discontinuity as well, which is I had that up here. So the x minus 1 equals 0, that is non-removable. Okay. Let's now focus our attention on one-sided limits. So the previous example, certainly it was not defined. Let's go back up to the continuity pictures here from the book. So if this is figure A, figure B, and this is figure C, figure B failed to be continuous for the last two qualities. The limit does not exist, and the limit does not equal, because the limit does not exist, the limit does not equal f of c. In particular, why did that limit fail to exist? Because the limit from one direction did not equal the limit from the other direction. You had, but you can kind of just restrict your attention to one particular approach, and that's what one-sided limits are about. Certainly a limit could fail, but you could always analyze the limit proceeding from one side, the limit approaching from one side. So one-sided limit, and we've kind of already done this, but we want to make it more clear. Okay, so again, another example. Let f of x equal this absolute value x over x, which will equal negative x over x, which equals -1 if x is less than 0, and then x over x, which equals 1 if x is greater than 0. And then our picture looks like this. Okay, so it's not defined at 0, so it's clearly not continuous. And not only that, it has a jump discontinuity. But you can kind of finesse some limits. Okay, so overall, the limit of f of x as x approaches 0 does not exist because it has different left-hand and right-hand behavior. Okay, but we can restrict our attention to one approach. So in particular, if you want to just look at the approach from the left. So that means coming in from the negative infinity side. I'm drawing it in red. As we approach 0 from the left, the y value is always -1. Okay, so we can say the limit of f of x as x goes to 0 from the left is -1. And then the limit of f of x as x approaches 0. And when I say from the left, I mean that little negative and the exponent in the bottom part of the limit. So there, under the LIM, it says x arrow 0, and you see that little negative? That means you're coming in from the left. Okay, so let me write that maybe over here. Approach from left. Okay. And then if you want to approach from the right, the way to notate that is to put a little plus sign instead in that in the exponent of the 0. Okay, so approach from the right, that's going to be this blue arrow I'm drawing. Okay, and the f of x values are always +1 approaching from that direction. So you could say that limit is 1. Okay. Okay, so great. Let's take a look at a couple examples of just finding one limit as opposed to the other, one side as opposed to the other. So let's look at an example. We have the limit as x goes to -3 from the left of x over square root of x squared minus 9. Okay. Okay. So if you do a substitution, what happens? So that's interesting to just kind of look at that. If you put a -3 into the numerator, you're going to get, well, -3. So you get -3 up here. But in the denominator, what's going on? You get -3 squared is 9, minus 9 is 0. Okay, so it's not, when you have something that causes division by 0, so if your limit, and I'll just write it to the top here, if your limit as x goes to whatever value c from the left or the right of this function is some number L, we'll call it L over 0, it's going to go in one of two places. It'll go really, really high, in other words, positive infinity, or it'll go really, really low to negative infinity. Okay, so that's, you know, your answer. You got a 50-50 chance at it. It's either positive infinity or negative infinity. Okay, so anyways, in this case, what I usually do is just a table of values, right? And we want to approach from the left. So you may want to draw a number line to remind yourself I'm approaching from the left. So I need numbers like -3 point, I don't know, 1, -3.01, and then I just want to see if it's getting really, really big negative or really, really big positive. 3.001. Maybe put them into your calculator. I did it earlier. So I'm getting 3.97, 12.98, negative, so it's a -12, -38.74, and maybe one more, -3.0001. And you kind of just look for the trend, right? So -122.48. So it seems like it's getting really, really big negative. So I put negative infinity. Okay. Okay, let's look at another one. So we have f of x equals this piecewise function, x plus 2 over 2. And that's if x is less than or equal to 3. And then 12 minus 2x over 3 if x is greater than 3. Okay, we want to see what happens exactly at 3. So when it's not 3, these two functions are continuous because they're just lines, equations of lines, and lines are continuous everywhere. You can always take the limit of x plus 2 over 2 for any c value that you want. Okay, so this thing is definitely, because it'll just end up being c plus 2 over 2. You could do a sub on it, right? And then likewise, as we approach c for 12 minus 2x over c. That's continuous everywhere because you could just plug it c in and you get 12 minus 2 times c over 2. So the only real question is it continuous? Is there a discontinuity at 3? Okay. In order to get around that, what we're going to kind of do is look at you could look at 3 and make sure it's the same on both sides, and we could also take a look at the limit as we approach. So f of 3, what is it? So it's 12 minus 6, so it's 6 over 3, which is 2. So we need to make sure the left and right hand limits also go the 2. So anyways, x approaches 3 from the left. We also need to look at limit as x approaches 3 from the right. As we approach from the left, we're looking at numbers less than 3. So we're using the first part of our function. As we approach 3 from the right, we're looking at the second half, the second piece of the function. Okay, so let's figure these out. X plus 2, so I could put in 3 here, so it'd be 5 halves. And then if I put in 3 into the other one, 12 minus 6 is 6. And then all over 3, which is 2. Okay, so it does not look like it's continuous because it has different left-hand and right-hand limits. So therefore, the limit as x approaches just plain old 3 of f of x does not exist. Okay, because it has different left and right-hand limits, and so it's defined at f of 3, but it's going to fail that second criteria for continuity from way back. So remember the 3 criteria. It has to be defined at c. This one was the limit of f of x has to exist, and that's where it fails big time. Okay. Let's look at another one. 20. This is another example. So limit as x goes to 3 from the right of the ln of x minus 3. So we wouldn't be able to take the limit of this in general because it's going to have an asymptote at 3. Right? 1, 2, 3 is its asymptote. And the graph is a logarithm, so it looks like this. Okay. So if we try to approach from the left, it's not defined anywhere, so that limit is not going to work. But we can figure out the limit coming in from the right. Okay, and so what is happening to the y values as we come in from the right? Well, you can kind of look at the value of the y values. So it's going like -1, negative maybe 2, -3, and it's going to keep going down and down and down and down. For any negative number you give me, I can find a number that is going to be below that number. Okay, and that's the definition of negative infinity. It just keeps on going down and down and down. Okay, more about continuity on intervals. So this is a painful piecewise approach to continuity, and it hopefully leaves you wanting a more global approach to continuity, which we have to just put off until later math classes. But here we will attempt to try to talk about continuity on a closed interval. Okay, continuity on closed interval. But it sounds better than what it really is. It's basically just a matter of having to, in addition, prove all of the continuity inside the interval. You have 2 extra limits at the endpoints, and the endpoint limits are going to be left and right hand limits that we have to worry about. So some closed interval from A to B, and the limit as x approaches c for any c in the interval must equal f of c. Okay. And then we also need these left and right hand limits as we approach the endpoints to work. Oh, my computer almost died on me. Limit as x approaches a from the right of f of x needs to be f of a. And then thirdly, the limit as x approaches b from the left of f of x has to equal f of b. Okay, so let's look at 35. And we're worried about the continuity of this function. It's a piecewise function, again, on the interval from -1 to 4. Okay, so first on the insides, because both pieces of the functions are equations of lines, we know we can do a substitution type limit, and those will be continuous for all values inside the interval except at 0. And I mean, we can even extend that to the endpoints. There's no reason to think that we wouldn't be able to work out the endpoints. I'll show you though, just in case you're skeptical. Okay. So at the endpoints, I have to make sure that as x approaches -1 from the right, and in that case, x is less than 0, so the piece we're working with is 3 minus x. Okay. So as we approach -1 from the right, we will have 3 minus -1, which equals 3 plus 1, which is 4. Which is equal to f of -1. Okay, f of -1, if you put that in there, look, the limit as x approaches 4 from the left, then we're on this piece of the function. So we could just do a substitution into the function, and clearly that's just going to be equal to f of 4. Okay, so we have 3 plus 1/2 times 4, which is equal to 3 plus 2, which is 5. And the way we figured that out was by doing substitution. So clearly that's just equal to f of 4. Okay, so anyways, all of that is established. There's just one issue. We need to make sure that the function is defined. Well, the function is, we need the continuity at that at 0. Maybe something weird happens there, right, because of the piecewise definition. So I sort of need to still check that. And so what were the criteria? So first, f of 0 has to be defined, and certainly when x is 0, it'll be 3 minus 0. So I'm on the first piece because x is less than or equal to 0. So it's defined. Secondly, I need that this limit as x approaches 0 of f of x to exist. Okay. So I could take a look at the left and right hand approaches to make sure that they both are the same. So as x approaches 0 from the left of f of x, so what is that? That would be numbers that are less than 0, so I'd be using the 3 minus x version. So that would be 3 minus 0, which is 3. And then I got to figure the limit as x goes to 0 from the right. So in that case, all the values I'm plugging in are greater than 0, so I use 3 plus 1/2 times x, and that'll equal 3. So I don't have this business with different left and right hand behaviors, so that limit does in fact exist. Okay. And then thirdly, I need to make sure that the limit as x approaches 0 of f of x actually equals f of 0. And of course it does in this case. It'll just be 3. Okay. So one thing I've been kind of using in the background here, which may or may not be obvious, is that if the limit from the left and the limit from the right are the same, then the limit exists, and the limit is equal to that number that the two limits is equal to. So where do I get that from? I do not pull things out of thin air. Okay, the fact that it's continuous at 0 is really because of theorem, I believe it's 2.10. Let me look in my book, make sure they didn't change it on me. Yeah. which basically says if the limit of f as x approaches c from the left equals some number L, and then that equals the limit of f as x approaches c from the right of f of x. That implies the limit of f of x as x approaches c also equals that L. Okay? We would still have to kind of finagle the issue that L is f of c, but clearly it is. So f of 0 above was 3, and then our limit was 3. Okay. Okay, so it works in both directions. So if you know that the limit of f of x as x approaches c is L, it also implies that the left and right hand limits will be L as well. Okay, so kind of an important theorem in this section that we'll use to establish continuity in these weird cases. Okay, properties of continuous functions. Note, let's call f of x e to the x, and g of x equals x squared. And note that these things are continuous. Okay. And then via theorem 2.11, the following functions will also be continuous. So a lot of calculus and a lot of math in general is just kind of like seeing what happens when you multiply two types of things together. Do I get the same type of thing, or does it transform it into something new? For example, if you multiply two counting numbers together, you get another counting number. Okay, like 2 times 2, or 3 times 2 equals 4. Okay. And that's always going to happen. If you add two counting numbers together, you're going to get another counting number, right? But if you subtract two counting numbers, you might not get another counting number. In fact, you'll get a negative number, which you can't count on your fingers, which is why I'm saying it's not a counting number. Okay. Likewise, if you divide two counting numbers, you're not going to get another counting number, always, right? In this case, 4/3 is not something you can count on your fingers. So we do the same thing with functions and continuity. If you take two continuous functions and you multiply them together, so it's called h sub 1 of x, is it also continuous, right? And yeah, it is. What about if I subtracted or added two continuous functions? Is that going to be continuous? Yes, it is. How about if I maybe multiplied one by a constant? Okay, so h1 of x equals 3x squared. Is that continuous? Well, yeah, it is. What about if I divided two continuous functions? Sort of, right? It's continuous everywhere except where the denominator is equal to 0. What about compositions then? Usually, right? So long as the outer function is continuous at every output of the inner function, and the inner function would also have to be well, we'll investigate that a little bit in the next problem. Okay, so, but for this case, f of g of x, which is equal to e to the x squared, that is continuous. Okay, okay, so let's look at an example where we have kind of a composition of two functions. So f of x is clearly not continuous at x equals 0. G of x equals x plus 1. Okay. We want to describe the continuity of the composition of f of g of x. Okay, so is that thing continuous at 0? You know, maybe that, you would think maybe that wouldn't be continuous. Well, let's look at it. So we make this new function h of x, and we're going to say that that's equal to f of g of x. Okay, and what is that? Well, that'll be 1 all over, and I put x plus 1 in for x. And then I take a look at it. Well, this thing is discontinuous, and it's a non-removable discontinuity. It's discontinuous at x equals 0, or -1, sorry. Okay, so doing this composition changes kind of how the f function is discontinuous. We got to make sure that f is continuous under the new kind of conditions. Okay, so doing compositions, yeah, it's you know, we have two functions, and yeah, so it can change where the discontinuity is kind of what I'm trying to say, I guess. Okay, so just be careful. I don't know. Okay, let's move on. I think I'm overthinking it. Okay, section 5, we get a high-powered theorem, the intermediate value theorem. Which is a pretty simple idea. Basically, if you have a continuous function on some closed interval, like a to maybe b here, and it starts at f of a, and f of a is maybe less than f of b, and it's continuous, that's going to mean that for any value in between f of a and f of b, there will exist some c value such that f of c will equal that particular value in between. So let's say I care about the value here at k. If this function is continuous from a to b, what's got to happen? Well, to get up to b, it's going to have to go through k eventually. Okay? And that's what this theorem is saying. It seems pretty obvious, but sometimes the things that are obvious need to be taken care of in math. Okay, we need to be very, very careful. All right, so anyways, let's actually write out the theorem in all of its glory. Theorem 2.13, if f is continuous on a closed interval from a to b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number c in the closed interval from a to b such that f of c is equal to that k value. All right, so one thing we could do with this theorem, and if you need to write that out, it's in the book. So usually I just say look in the book, but there it is. We want to be very careful about how we use these things. It won't apply if you don't have continuity on this closed interval, and you know you have to have these three criteria hold for it to work. Let's look at an example, right? So where would this be applied? F of x equals x cubed plus x minus 1. And what's going on here? I'm looking for whether or not this thing has a 0 on the interval from 0 to 5. Right? Why would I care? Well, look, if you try to factor this thing, if you try to solve this, you will fail miserably. Okay, at least I think 90% of you will. The problem is we don't really know how to factor cubics like maybe our ancestors did. I think maybe this is called a depressed cubic or something like that. There are methods for factoring it, but we don't teach them. So for most of us, we probably not heard of that, and we don't know how to factor this, so we wouldn't know how to solve this, and we wouldn't even know if it had a 0 in there to begin with, right? But we note f is continuous, so it's a polynomial, so it is continuous on the closed interval from 0 to 5. Secondly, f of 0, if you plug 0 into the function, you're going to get -1. And that won't be the same as f of 5. If you plug 5 in there, you get 129. Okay? And then thirdly, f of 0 is, so what am I doing here? I'm trying to establish the three criteria that you need for this theorem to apply. So first, I have to show that f is continuous, right? Secondly, I have to show that f of a is not equal to f of b. And then thirdly, I want this k value to be a number in between, has to be a number between f of a and f of b. So note f of 0 is -1. F of 0 is -1, which is less than 0, which is less than f of 5, which is 129. Okay, so what I'm doing is saying that all three of these criteria that you need in the theorem are holding. So therefore, there is at least one number c in the interval such that f of c is equal to 0. Okay, so from then, trying to get my eraser to work. From the intermediate value theorem, we can conclude there must be a c value in the interval from 0 to 5 such that f of c equals 0. Okay, so you know the question: does f of x have any zeros in this interval? Yes. Okay. So you know that makes life easier. So imagine you're looking for a needle in a haystack. What if you didn't know there was a needle in that haystack? So a lot of these math theorems kind of help us in that respect. It's like you're not going on a suicide mission if you're looking for this 0. And knowing that is nice because there are a lot of problems in mathematics where you have no idea if you are going to be able to solve it. And there's people that spend their entire lives looking for answers and never find them. You know, they die poor and alone and unfulfilled, right? So at least in this case, if you can find that the needle is actually in the haystack, you will be, you know, you're on to something. You know, it's not going to be a fruitless endeavor. Okay, so I'll leave you at that, and I'll see you next time.